In the next part of Chapter 12, we want to look at the different types of intermolecular forces that exist between molecules or atoms of a substance. So rather than talking about the bonds that hold atoms together within the molecule, we're talking about the forces that hold them together in a liquid or solid state. And the three types of intermolecular forces that we want to focus on are the dispersion forces, dipole-dipole interactions, and hydrogen bonding. Now, when we're talking about intermolecular forces, the thing to know is that strong intermolecular forces will result in liquids and solids that have typically high melting and high boiling points, relatively speaking. If we have very weak intermolecular forces, then we're probably talking about gases, things that have very low melting, very low boiling points. Okay, so if we look at those three types of intermolecular forces that I mentioned, if we go in order of increasing strength, you're going to start with dispersion forces as the weakest forces holding molecules together, dipole-dipole interactions, and then hydrogen bonds. So let's start with the dispersion forces. This is sort of the default intermolecular force. This is something that all molecules and atoms have. So if they have no other forces between them, this is the one that they have to kind of hold them together. And these are also known as London forces, so you may hear it called that as well. Now, dispersion forces are going to be caused by a fluctuation in the distribution of electrons within the molecule or the atom. So all atoms, all molecules have electrons, and so the way that those electrons get dispersed create these dispersion forces. Okay, so that's why dispersion. The electrons in an atom or molecule might at any given instant be unevenly distributed. Now that doesn't mean they're that way all the time, but it means that something can disrupt that pattern and create an uneven dispersion of electrons, and that creates forces, temporary dipoles, that can hold these molecules together. Okay, so if you look at the figure here, for instance, if you looked at an atom of helium, helium has 2 electrons. So in the first frame, you can see one placement for the electrons. Well, frame number 2, if we took a snapshot at some other time, you might see that distribution of electrons. And then frame 3, you can see that the electrons have temporarily displaced themselves on, in the same area of that shell around that nucleus. And so when those electrons get close enough together to do that, they're creating this temporary dipole, this temporary net negative charge, temporary net positive charge. And that gives them momentary dipole interactions that can hold them together, temporary sort of magnetic forces. Dispersion forces, looking at the history of that, were first recognized by Fritz London, a German-American physicist, and that's where the idea of London forces comes from. They were named after the scientist who first described them. Now, when you've got that temporary charge separation, that temporary dipole that I mentioned, that's also known as an instantaneous dipole. It's not permanent, it's not there all the time, it just happened at a particular instant for that molecule or atom. So for instance, in the figure that we just saw, an instantaneous dipole on one helium atom can induce an instantaneous dipole on a neighboring atom. So when you create that temporary charge, that can actually affect the electrons in the neighboring atoms or molecules and create temporary dipoles in those as well. And so when that happens, all the neighboring atoms become attracted to one another that way. They line up just like magnets. Positive end of one instantaneous dipole attracts the negative end of the other, and you get these forces that can kind of help hold this thing together. So the thing to remember about dispersion forces is that the dipoles that create this attraction are fleeting. They are transient. They don't stay that way all the time. So they constantly appear and disappear in response to a fluctuation in an electron cloud. So you can influence these externally as well. You can influence those dipole or dispersion interactions. All right, so a dispersion force, looking at that, you've got an instantaneous dipole, again going to helium atoms. Okay, if we want to look at this in terms of a visual representation, if we got this lining up at the electrons, a temporary negative here and a temporary positive, the positive on this one can actually cause the electrons in the neighboring atom to pull to this direction, creating dipoles again, and that can then affect this one, pulling the electrons in this way. And so you get this chain reaction going, and then what you get are these weak attractions between the negative and positive charges between those atoms. But it's a very weak interaction. Now, how weak is it? What is the magnitude of that? Well, that depends on how easily the electrons that are in that atom or molecule can polarize, can be polarized in response to that instantaneous dipole. That is dependent upon the size of the electron cloud. So how big is the cloud? How many electrons do you have in there? So when we say polarize, all we're talking about is forming one of those dipole moments. If you've got a very large electron cloud, then you're going to get greater dispersion forces because the electrons are not being held as tightly by the nucleus. They're further away and they're not seeing as much pull from the nucleus, from the positive charge in the nucleus of the atom. And so those can be polarized a little bit more easily. Okay, now molar mass alone it's not the only factor to determine how big your dispersion forces will be, but in general we can use that as a guide to compare dispersion forces. So if you want to look at trends in the periodic table, you can base that on size or molar mass. So for example, in table 12.4 that you have in your book, it talks about the boiling point of the noble gases. And remember, noble gases are very stable atoms, stable molecules for the ones that are diatomic. And if we look at those boiling points and we look at the change in boiling point with the change in molar mass, we can see, looking down the periodic table, starting with helium, that's the smallest one, and then neon, argon, krypton, xenon, you're getting larger as you go. Molar mass is getting higher, so you go 4, 20, 40, 84, 131. They're getting larger as you go. Now look at the boiling points. 4.2 Kelvin, 27 Kelvin, 87 Kelvin. Okay, so those are increasing as well. So you're seeing that same effect in the trend. So summarizing dipole-dipole forces. They exist in all, this is dipole-dipole. So those were dispersion forces. Everything has those. Now, dipole-dipole, you're going to have for polar molecules. So nonpolar molecules will not have a dipole-dipole force. They will have dispersion forces. But when you have a polar molecule, remember, that's an uneven distribution of the electronegativity within that molecule. And so when that happens, you create a permanent dipole within that molecule. That's what makes them polar. They have a permanent dipole that is always there. There's one end that's always a partial positive, one end that's always a partial negative. And that allows these molecules to interact with one another a little bit more strongly than you would have with just dispersion forces, because the forces aren't temporary, they're there all the time. Okay? So polar molecules will have dipole-dipole forces and dispersion forces. Now, because they've got more forces interacting on them and a little bit stronger forces, this raises the melting point and the boiling point relative to the nonpolar molecules that we've looked at. If you look at ones that have similar molar mass, the polar ones are going to have these higher temperatures. So for example, if we look at a molecule such as formaldehyde down here, so CH2O. Okay, this is a polar molecule. So we've got this partial negative down here with the oxygens, so higher electronegativity, electrons are pulled down there. Partial positive down toward the hydrogens. Okay, again, looking at the molecular geometry here. Okay, permanent dipole. And so the positive end of one of the molecules will be attracted to the negative end of the neighboring molecule. And that's where you're going to get your dipole-dipole force. Notice it looks just like the dispersion force, but the thing is that it's not temporary. It's there all the time. Looking at that effect, again, we can see the effect on the boiling points and melting points for those compounds. If we look at formaldehyde, which we said is polar, okay, and we compare that to ethane, which is nonpolar. Look at their molar masses. The molar masses are almost identical, around 30 grams per mole. You can see the differences in the structure here. Now look at the boiling point, negative 19.5 for the formaldehyde versus negative 88 for the ethane. So that actually, again, you have to think in terms of negative numbers. That's quite a bit higher temperature for the formaldehyde. It has to be quite a bit warmer than the ethane in order to boil. And again, negative 92 versus negative 172. Again, it's a higher melting point for formaldehyde than it is for ethane. So that is because of the dipole-dipole interactions that you have in the formaldehyde. Looking at those dipole-dipole interactions, something else we want to look at is the idea of the miscibility of liquids. So when you start getting into dipole-dipole interactions, you get interactions that are strong enough to hold things together and create solids and liquids. So miscibility is going to be a liquid's ability to mix with another liquid without separating into two phases. So in other words, does one liquid have the ability to dissolve into the other liquid? In general, polar liquids are going to be miscible with other polar liquids, like dissolves like, but they tend not to be miscible with a nonpolar liquid. So oil and water. Water is polar, oil is nonpolar. They don't mix, so oil is not miscible in water. So that's why if you have oil on your hands or you have these oily stains on clothes, you can't just wash that away with plain water. If you've ever gotten grease or butter or anything like that on your hands and then try to wash your hands just using water, all you're doing is spreading the oil around. You have to have something to break that up. All right, so polar and nonpolar compounds, if we look at some examples of that, here's some images of polar and nonpolar, how they don't mix, they're not miscible. In the first one, there's a representation of pentane, which is the molecule that is being shown, poured on top here, does not mix well with the water on the bottom. So you pour them together, you give them a chance to settle out, and you'll see the layer in between. Same thing in the next one. Mix oil and vinegar. So vinegar is a water-based solution. Mix them together and let them sit, and you'll see that dividing line. In the last image, you see oil spilled from a tanker. So you can see the oil slicks that are floating on top of the water. They don't dissolve into the water. They just spread out on the water. So, how do you determine if a molecule has dipole-dipole forces, if it's a polar molecule? So, first, determine whether the molecule is polar. So look at the individual bonds in the molecule and determine if they are polar or not. And then determine whether the polar bonds add together to give you a net dipole. So we've already looked at this, and what you're looking for is, do the forces cancel each other out, or do they give you a net charge in one direction? And some examples are shown here, but we've already gone through that. All right, the last type of intermolecular force that we're going to talk about here is hydrogen bonding. Now, polar molecules sometimes contain hydrogen atoms that are bonded directly to highly electronegative atoms such as fluorine, oxygen, or nitrogen. When you have that particular situation, when you have a hydrogen atom bonded directly to one of those three, fluorine, oxygen, or nitrogen, this will exhibit an additional intermolecular force called a hydrogen bond. Now, a hydrogen bond is still a dipole-dipole force, but it's a special kind of dipole-dipole, sometimes called a super dipole-dipole force. It's just a very, very strong dipole-dipole interaction. Some examples of molecules that will undergo this hydrogen bonding: hydrogen fluoride, HF, hydrofluoric acid; ammonia, NH3, so remember you've got 3 of those hydrogen bonds to the nitrogen; H2O. All of those are common substances that undergo hydrogen bonding. Okay, so the reason for that, as we said, a large electronegativity difference between hydrogen and those molecules. The other thing that helps is the relatively small size of these atoms. Notice they're all right up near the top of the periodic table. They're not big, bulky atoms. They're fairly small. Because of that, it allows the neighboring molecules to get very close to those atoms or the molecules created from those atoms. So they can get very close together, and they have very strong dipole-dipole interactions because of that high electronegativity difference. And so that creates a fairly strong bond. So looking at an example, if we lined up hydrofluoric acid molecules, hydrogen fluoride molecules, and we can see our partial positive and partial negative. Well, these are almost like, plus plus and minus minus. They're just short of being an ionic bond here. They're fairly strongly separated. And so if I get this negative attraction connecting to this positive on the next one, I get a bond here that is fairly strong and fairly short. Now, when I say bond, I'm not talking like a bond between atoms, but this force that kind of holds the molecules together. These are hydrogen bonds. Another example of a material that can hydrogen bond is methanol. So it's an alcohol. You've got a carbon bonded to 3 hydrogens here, 1, 2, 3, and then it's bonded to an oxygen, which in turn has another hydrogen. Okay. Now, since methanol contains hydrogen atoms which are directly bonded to oxygen, right here, this one, then it can form hydrogen bonds to the next one. So it's the OH group that is particularly important in this alcohol to allow hydrogen bonding. Okay, so right here we form a hydrogen bond. Now, if we look at the effects of hydrogen bonding on melting points and boiling points for 2 compounds that have similar molecular masses, okay, again, here's an alcohol, has hydrogen bonding, here's ethane, that is a nonpolar molecule, it's only got dispersion forces. Very similar molar masses. Okay, we still have these values from before. Now look at the melting point and boiling point for methanol. Not only are they quite a bit higher than they are for ethane, but we're actually in the positive end of things for methanol. So its boiling point, it's a liquid at room temperature, and so you've got to actually warm it up a little to get it to boil. Okay, so big effect on strengthening those interactions, and this will become very important to you when you take organic chemistry. It's very important to understand that because you rely a lot on melting points and boiling points and molar masses to help you identify these compounds and identify their properties and how they're going to react. And then we also want to mention water as a special case because water has hydrogen bonding, which is one of many reasons why water is such a remarkable molecule. Water molecules form particularly strong hydrogen bonds with each other. And that's why we have surface tension, why we have a variety of properties for water. Boiling point of water is high, remarkably high for a molecule with a low molar mass. Its molar mass is only about 18 grams per mole, but its boiling point is 100 degrees Celsius. That's fairly unusual for smaller molecules. This also gives water the property of being able to work as such a good solvent and dissolve so many things. So for example, if we look at the ion dipole forces that exist between sodium and water molecules. So it's sodium chloride. How does salt dissolve in water? So sodium positive ions line up with the negatives, the partial negatives in the water, and then same thing for chlorine, but it's the opposite. So notice here on this side how all the molecules are lined up with the oxygens to the inside, the red molecule. Here they're lined up with the hydrogens to the inside, the white ones. But that property of the hydrogen bonding, those very strong dipole-dipole interactions, allows it to interact with the ions that you find in an ionic solid and kind of help to pull those apart and dissolve those. So table 12.5 gives you a summary of all the different types of intermolecular forces that we've talked about here. So you've got dispersion forces at the very beginning. It's a weak force, but it increases with molar mass, and all atoms and molecules have this force. You've got dipole-dipole forces, which are moderately strong forces. Only polar molecules will have those. You have hydrogen bonding, which is a strong intermolecular force, and that is specific to molecules that have hydrogen bonded directly to fluorine, oxygen, or nitrogen. And then we also want to look at this ion-dipole interaction. Okay, it's a very strong intermolecular force. So if it weren't a stronger force than the hydrogen bonding, then water molecules would have no reason to interact with these ions. They would just continue interacting with each other. But because that ion-dipole interaction is stronger, then we get this other situation happening where we get a mixture of ionic compounds as ions and polar compounds. We also want to look at solids. Most of what we've looked at so far have been liquids, so we want to touch on types of crystalline solids. So types of crystalline solids that you can have are molecular, ionic, and atomic. Now, what are we talking about when we talk about a crystalline solid? Well, we're talking about something that has a highly ordered structural array of atoms and molecules. The sort of opposite of a crystalline solid is an amorphous solid, so one that doesn't have a long-range order. It doesn't have a pattern to it, if you will. So an example of an amorphous solid is glass. The molecules in that one are not arranged in an orderly fashion. There isn't a way to cleave or break that apart along this line. All right, so crystalline solids, we said there are three types: molecular, ionic, and atomic. And this is based on the individual units that make up the solid. So let's take a look at those. So molecular solids are the composite units for molecular solids are molecules. So it's just an orderly arrangement of molecules of one type. And these tend to have relatively low melting points, such as ice. So if we take water molecules and remove enough energy that they go into the solid form, they arrange themselves in a very orderly pattern. And this is why ice actually expands. We already talked about this in another chapter, that most liquids, when you freeze them and cool them down, they condense. They draw in closer. Water is one of the exceptions because of this structuring, this crystalline structure that the water molecules undergo when they become ice, when they go into the solid form. You can have ionic solids, okay, number 2 here, that are composed of formula units. This is what we talked about way back at the beginning of the semester, cations and anions that come together. So ionic forces holding them together, very high melting points, such as table salt. Now, table salt can be very easily dissolved in water because of those ion-dipole interactions, but if you just wanted to take some salt and melt it, put it in a pan, add heat until it becomes a liquid, you'll find that it takes a lot of heat to do that. You're not going to be able to do it on your kitchen stove. And then the last one over here are atomic solids, and these are just the composite units that you get when you put together atoms of one particular type. Metals generally is what you're talking about. And the melting point will be variable depending on the properties of that material, of the metal, or, I mean, it can be non-metals as well, but if you're talking about more or less pure elements. Starting with the molecular solids, just sort of running back through some of the things we've said. Okay, composite units are molecules. So we talked about ice. Dry ice is another example of that, where we take carbon dioxide molecules and cool them down until they go into the solid form, put pressure on it as well. Okay, those are molecular solids. What's holding those together are the intermolecular forces, and it can be any of the three intermolecular forces. For instance, ice is held together by hydrogen bonds, but dry ice is held together with just dispersion forces. It's a nonpolar molecule, so it's very weak dispersion forces. That's why it takes a little bit more energy to melt a piece of ice as opposed to sublimating a piece of dry ice. Dry ice tends to sublimate very quickly. So molecular solids, on the whole, tend to have fairly low melting points, low, moderately low. So we know ice melts at 0 degrees Celsius. Dry ice, it's negative 78 degrees Celsius where it starts subliming. All right, ionic solids, we said, composed of formula units. So we have cations and anions that come together. Table salt we looked at, calcium fluoride, any of the salts we looked at. Lots of good examples of ionic solids. And those are being held together by electrostatic attraction. So this was where we actually had a transfer of electrons from one atom to another, created an ion, permanent ion charge, cations and anions that are then held together by that strong force. Okay, now when you take these ionic solids and bring those cations and anions together, you create a solid lattice because you get an alternating pattern of cations and anions in 3 dimensions. So we can think of 2 of them coming together, but then keep in mind that as you bring more of these formula units together, they're going to line themselves up in an orderly fashion. So for example, sodium chloride lines itself up in cubes. The forces that hold these ionic solids together are actually ionic bonds. So this is where we're talking about actual bonds holding these things together. Ionic bonds are much stronger than any of the intermolecular forces we've looked at. And this is what gives ionic solids their property of having very high melting points compared to molecular solids. So remember I said that table salt, if you wanted to melt it, you're probably not going to be able to do that with your home stove. Okay, it melts at about 800 degrees Celsius. That's Celsius, not Fahrenheit. Carbon disulfide, which is a molecular solid, which has a higher molar mass than sodium chloride, melts at a negative 110 degrees Celsius. So it's really, really hard to get carbon disulfide in its solid form. You've got to get it really, really cold. Okay, atomic solids, touching on that again, okay, these are individual atoms. So these are materials made up of only one element. So diamond is an example of that, and conversely graphite. Okay, so diamond and graphite are both just pure carbon. They're just in different forms. Iron, if you have a piece of iron metal, again, you know, can vary in purity, but if it's pure iron metal, that's an atomic solid. You can actually have solid xenon, although it typically exists as a gas, but you can get those. Atomic solids can be divided into 3 categories. So we're dividing and subdividing here. But if you're talking about an atomic solid with an element, you can have covalent atomic solids, non-bonding atomic solids, and metallic atomic solids. Okay, and there's a slightly different force for all of those. The metallic is the most common, of course. All right, so there's your summary of atomic solids. So we said we have covalent, and as the name implies, it's being held together by covalent bonds. These tend to have high melting points. So for instance, something like silicon. So if you look at silicon atoms that are bonded together, they don't pull electrons away from each other, they share those electrons, so covalent bonding. You have a non-bonding atomic solid. So if we look at that solid xenon that we mentioned earlier, there are only dispersion forces holding that together. These are weak forces, so low melting points, weak forces. Okay, strong over here, strong covalent. Okay, and then you have metallic, okay, which are being held together by metallic bonds. And it's just, again, you know, it could be ionic, it could be covalent. It depends on the metal itself. They're metallic bonds, and depending, again, on the particular metal, the type of metallic bond it has, you'll get these variable melting points. So you can't really say, generally speaking, what kind of melting point you're going to have with a metal. So looking at the example of diamond. So we said that a diamond is held together by covalent bonds. So what's happening is every carbon atom is going to form 4 covalent bonds to 4 other carbon atoms in that tetrahedral geometry that we looked at. Whoops, sorry, went too far there. Got off the screen. So now this carbon atom here is bonded that way. Well, now if we take this one and we keep going, it's bonded down there, and then it can have one here, one here, one here, and it just keeps going in this arrangement. So you can just imagine it spreading out that way, and it's forming this lattice. So the entire crystal kind of forms this tetrahedral lattice that if you've ever seen a diamond, you can see that tetrahedral geometry played out on a macroscopic scale. If you've ever seen one that's uncut, that is in its natural state as it grew. Okay. Basically, a diamond crystal is just one giant molecule that's held together by covalent bonds. It's going to keep that tetrahedral structure and just multiply it. It just grows from that, basically. Okay, so covalent bonds, very strong. So high melting points, as we said. What if you wanted to melt a diamond? Well, sodium chloride took 800 degrees Celsius. We don't really know with diamond, but we estimate that it's going to take about 3,800 degrees Celsius to melt a diamond. We can't really do that very easily. Okay. So if we could take a diamond and look at it on a microscopic scale, we'd see a structure that looks something like this. This is a little bit easier to see than what I drew on the last slide. So you can see that orderly pattern of tetrahedrons hooking together and growing and forming a lattice. So again, they're showing just a small portion here, but now imagine, all of these carbon atoms on the outside, they're going to continue that pattern. They're going to continue hooking together and creating this lattice and growing. All right, going to the non-bonding atomic solids, like the solid xenon. We said these are only dispersion forces. These tend to be relatively weak. So, for example, xenon atoms, they have a stable electron configuration already. They don't want to form covalent bonds, or for that matter, any kind of bond with each other. So they've only got these very weak dispersion forces. So solid xenon is going to have a very low melting point. Okay, about negative 112 degrees Celsius. So as I said, solid xenon is a little bit hard to come by. It's not its natural state at room temperature for sure. Metallic atomic solids. So all the metals on the periodic table, iron, silver, lead, copper, any of those, tin, they all have a variable melting point. There's no way to say, oh, they're all going to be around this. They're all going to be in the thousands. They're all going to be negative. It just depends on the metal. They're held together by positively charged ions in a sea of electrons. Okay, so it's just these positive charges floating around in this delocalized sea of electrons in the metal. So depending on the ratio of positive charges to amount of sea of electrons, you get bonds of varying strength. So for instance, mercury has a melting point below that of room temperature, negative 39 degrees Celsius. Mercury is the only metal that's a liquid at room temperature. You have other metals like iron that have very high melting points, relatively speaking. It's about 1800 degrees Celsius to melt iron. So you get a wide range of melting points and boiling points for metallic atomic solids. So when we're talking about that positive charge in a sea of electrons, what are we talking about? Okay, here's a figure just to sort of illustrate that. So each atom donates one or more electrons to this sea. These electrons sort of move freely throughout this metal structure, which is why metals are good conductors of electricity. They have this sea of electrons that are available to sort of transmit a charge. So if I bring this negative charge, if I bring this electron or electricity in here, it can bump in and it can create a cascade reaction. So this electron can bump into this one, move it down here, it can bump down to that one and down to that one. And so the electrons keep moving until eventually electrons come out, the other side of your metal or wire or whatever you've got. It just moves this charge down through the sea of these electrons. And going back to water, we've talked about the water's properties, how amazing water is. Okay, so we already said it has a low molar mass, but it's a liquid, not a gas at room temperature. That's very unusual. Okay, it has a relatively high boiling point. Okay, and if we want to understand why it has this high boiling point compared to similar molecules of the same, molar mass, same class, okay, we look at the structure of the molecule. So we look at the dipole that's created, the partial negative, the partial positives down here along this one, and the fact that it's very electronegative, that it has hydrogen bonding. So we have the geometry of the water molecule, which is bent, okay, and we have these highly polar oxygen-hydrogen bonds. So we get hydrogen bonding. Okay. That high polarity gives it a high boiling point. It also gives it the ability to dissolve a lot of other compounds. It's a great universal solvent. Okay. Because of these properties, because of the bent geometry, and because of the hydrogen bonding that we find in water, water acts as universal solvent. It really is. It dissolves so many things. It's the main solvent for living organisms. We've incorporated that into our very beings. Excuse me. So water is used to transport nutrients, hormones, all the compounds you need in your body are in an aqueous system. Your blood is basically just salty water with some other stuff thrown in there. Lots and lots of water. Okay. So life is impossible without water, and so if we look on Earth, if there's water available, there's usually some kind of life there. Places that are devoid of life are usually devoid of water. So that's the big push for looking for water on other planets. That's why it's such a big deal looking for evidence of water on Mars. And we know this. We know that we need water to survive, but we may not truly appreciate how remarkable water is. We can find lots of planets that have liquids on them, but liquid doesn't do us any good. It can't just be any liquid. We really need it to be water with those remarkable, amazing properties that it has. So we've talked about so many things that make water unusual. The way water freezes. We said because when it freezes, it creates that crystalline structure, spaces itself out, so it expands when it freezes. Because it expands when it freezes, it's less dense. Usually, as a liquid freezes, the solid sinks to the bottom. It's more dense than the liquid. Well, ice is the opposite. Water will continue to get more dense as it cools off. So colder water will sink down and creates what we call thermoclines and things like that. You may be familiar with that idea. But that only goes until about 4 degrees Celsius. That's where water reaches its maximum density, and once it starts cooling down below 4 degrees Celsius, this is where it starts to arrange itself in that pattern, it starts to spread out, and it becomes less dense. So it continues to spread itself out, it continues rising, so you'll actually find 3 degrees Celsius water at a higher level in a pond or lake than you will 4 degrees Celsius water. Okay, that's the coldest it's going to get. That would be down at the bottom. So that's, going deep. So as it starts expanding and it gets colder and colder, eventually it hits 0 degrees Celsius and it locks itself into a solid pattern. It freezes, and those rise to the surface. Ice cubes, icebergs, anything like that float. When a winter lake freezes, frozen layer of ice over the top, not only does that layer kind of float at the top, it also kind of helps lock in the water underneath it. So it kind of insulates it and prevents the lake from freezing further. And this is very important to us as a species as well, because if the ice layer didn't come to the top, if it sank, it would tend to kill bottom-dwelling fish and other aquatic life. It would allow a lake possibly to freeze solid. So we know that usually there's just a layer on top that's frozen, there's liquid water underneath, if it happened the other way, the whole thing could freeze and probably would freeze. So aquatic life would either be forced to the surface and they would have to exist in an exposed condition on the surface, or it would just be frozen solid. So we would probably not have any aquatic life if it were not for the fact that ice floats. That expansion of water when it freezes is also one of the reasons that organisms don't survive being frozen. Why we have to prevent freezing of our cells, because our cells are full of water, and if the water freezes, it expands, it has a crystalline structure, and it ruptures the cell. It's just like bursting a pipe when water freezes, or if you leave your water bottle in the freezer too long and it bursts open. Cells are going to do the same thing. Foods, plant materials, the same way. So many foods don't survive freezing very well, okay, especially those with a high water content. So certain things can freeze, but you have to do it in the right way. So like industrially prepared fruits and vegetables, they are flash frozen. Flash freezing goes so quickly that the water molecules don't really have time to align themselves up in their expanded phase. They don't really spread out as much, and so it doesn't rupture the cells of that frozen fruit or vegetable. But if you just let them freeze slowly over time and there's a high water content, chances are your food isn't going to fare very well. This is why we don't freeze a lot of things like squash and cucumbers. They have such a high water content that it just destroys the cellular structure of those materials when you freeze it, and then you thaw it back out and the cells just collapse. It's not very pleasant. All right, so that wraps up Chapter 12. You've got your review of Chapter 12, and then the last bit that we'll look at will be Chapter 14.